Consider the system of equations below. So we have x plus 3y plus m squared minus 2mz is equal to n squared plus 1. X plus y plus mz is equal to 1. And x plus y plus m squared minus 4m plus 6z is equal to n squared minus 3. Reduce the system of equations by eliminating x and y. So if I call these equations 1, 2, and 3, and I'm going to start by doing equation 1, take away equation 2, which will eliminate x. So x take away x, then 3y take away y is 2y. And then I've got m squared minus 2mz take away mz. That's going to give me m squared minus 3mz. And that is going to be equal to n squared plus 1 take away 1, which is n squared. Let's call that one equation 4. Now if I do 1 take away 3, again the x's are going to go. 3y take away y, that one is 2y. And then we've got m squared minus 2m z's take away m squared minus 4m plus 6 z's. So take out the z, and we have m squared minus 2m minus m squared plus 4m minus 6. And so we can see that that is z into the m squareds will go, and it is going to be 2m take away 6. So we have 2m take away 6z is n squared plus 1 take away n squared take away 3, which is n squared plus 1 take n squared plus 3, and so that is equal to 4. And let's call that equation 5. We can then do equation 4 take away equation 5, since both of those equations have 2y. And then we'll have m squared minus 3mz take away, correction, there's 3 m's there, isn't there? M squared minus 3mz take away 2m minus 6z equals n squared minus 4. And tidying that up gives me m squared minus 5m plus 6 z's is equal to n squared take away 4. Now I could write this as m minus 3 m minus 2 z's is equal to n minus 2 n plus 2. So we now want to state the value or values of m and n. So the system has, firstly, a unique solution. Well, all we need for that is for this coefficient to not be 0. So that is just going to be m is not equal to 2 or 3. We now want no solutions. And that means we want a situation where we have 0 z's is equal to, say, a, where a is not 0, and then that is not possible. So for no solutions, we would have m equal to 2 or 3, and n not equal to plus or minus 2. So 2 or minus 2 will make this side 0. We want it to not be 0. And then finally, we want an infinite number of solutions. Well, that's a situation where we want 0z to be equal to 0. So that would be that m is 2 or 3, making the left-hand side 0, and n is equal to plus or minus 2. Might be worth just looking at a couple of these situations and seeing what they look like further up in the solution. So let's just, for example, take m equal to 2 and see what happens further up, say when we get equations 4 and 5. So with m equal to 2, what would we get? We'd have 2y plus 4 minus 6, so actually minus 2 z's, and let's just take n equal to anything because it was just not equal to plus or minus 2. Let's take n is equal to 3 or something, and then that would be 9. And then if we look at equation 5, we'd have 2y, and then we'd have 4 take away 6, so minus 2z is equal to 4. And we can see that those are inconsistent equations. And so it very much looks like that one would be a Toblerone box. If we look at a different situation, such as the unique solution, so that just says that m is not equal to 2 or 3. Let's just take m equal to something like, I don't know, 1. So if we had m equal to 1, say, and we go back up, then what happens to equations 4 and 5? So we would have 2y and 1 take away 3, so minus 2z is equal to, let's just take in a value like 3 again, so let's just say it's 9. And then we would have here 2y, and that would be minus 4z's is equal to 4. And we can see that that system could be solved to get a unique solution. And finally, for the infinite number of solutions, let's take m equal to 2, and let's say n equal to 2 as